application of science. So Sudhanshu will talk about Anderson Enigma in disordered superconductors.
Indeed, privileged to talk in this conference in celebration of Professor T.V. Ramakrishna's birthday. So I am honored in that and thankful to the organizers to give me opportunity to talk in this conference. So I was very fortunate to be associated with Professor T.V. Ramakrishnan as a postdoc in IISc for 3 years. And during these 3 years, he enlisted kind of or obtained problems to me, and I attempted most of them, but I could solve those problems successfully only 2. But what I have learned from him, to the extent I could do, is to understand the problems microscopically to understand the phenomena in condensed matter systems. So today I will talk on Anderson theorem on disordered superconductors, and I'll show some puzzle in this theorem. So that is me.
So this is the other Anderson's theorem.
Right. So. Okay, I will do this from here. And some other themes as a part of the introduction. Then I will motivate the problem that I am going to study. It's basically the superconductivity. I mean the reduction of superconducting transition temperature with the disorder. So in my study, what I will do is some kind of correlated fluctuation in the order parameter, and I will show that because of that there will be some kind of lifetime of Cooper pairs, scattering lifetime, and I will estimate that. And on the process that I will show that is responsible for the reduction of the order parameter with disorder as well as critical temperature, and I will compare those critical temperatures with the experiments that Pratap showed us day before the study. And then I will also show the density of states calculations, and then will show that there is a shifting of coherence peak with disorder, and finally I will conclude. So for students, so I will just describe briefly the Anderson theorem. So in a non-magnetic disorder, BCS superconductor, an electron forms Cooper pair with its time reverse partner. As you all know that even in BCS theory that the Cooper pairs are time reverse partners, because one at momentum k with up spin and other with momentum at minus k with down spin. Now in presence of disorder, so you can solve this Hamiltonian disorder. So this is the eigenstate, the eigenvalues. So these time reversed wave functions also the eigenstate of that Hamiltonian. So these are degenerate, and those exact eigenstates is the linear combination of the block eigenstates phi k, and this is the time reversed wave functions. And so the exact wave function you can write in terms of the blocked eigenstates. Now the superconducting interacting Hamiltonian that you can write in terms of these exact eigenstates. So these are these creation operator which says that you create an electron with the up spin in the eigenstates psi n, and this corresponds to you create an electron with down spin in the eigenstate of psi n star. So in that basis, so electron phonon interactions that you can write in terms of this nk, the matrix elements, and so these are the phononic interaction. So as BCS theory approximated, these are constants, the m's and omegas, the frequencies. And if you take that approximations and then from normalizations n k mod square is 1, then you can see that Bn n prime which is a constant. So Anderson argued that this interaction is a constant as it is for the plane wave states. So since this interaction is constant, so immediate conclusion is that the order parameter is, as well as the critical temperature, is independent of disorder. So around the same times, Gorkov has perturbative calculation. So I'll just quickly go through that. So this is the action for the superconductor in the presence of disorder. So that is the disorder potential Vr, and this is the superconducting order parameters delta R and delta star R. And so we have the equations for the order parameters delta star R. This is the interaction, and in terms of the Gorkov's anomalous Green's function f. Now, so one can solve that using the Gorkov's equations. So you can express this anomalous Green's function in terms of the normal Green's function g, then delta star and gr prime r. And then you could take the configuration average for the order parameter. So that is the delta star r prime. And then you take the approximation that you average only delta star r prime, and then average the two Green's functions. And if you want to calculate the critical temperatures, so instead of the Gorkov's normal Green's function, you can take that simply the metallic Green's function g and this. So that is the approximations, and then one can calculate this pair correlation function, and what one gets is that you can get Tc from this equation, which is this pair correlation function. So pair correlation functions is essentially you take the all kinds of scattering in the ladder approximation. So that is this thing, and this is the pair correlation functions that you can calculate. Is depends on pair correlation function depends on the disorder, because that is the elapsed time is coming tau e, scattering time rather. And then so this is the normal Green's function, and then if you calculate all basically vertex corrections, then you get the full pair correlation functions, and so in turn that is actually independent of disorder. So as if the equation that you find is in the absence of disorder. So in the absence of disorder, that we know that critical temperature is this from the BCS theory, and same equation that we find from this equation. So there is no correction to Tc up to order on our kf. Kf is the Fermi momentum and L is the scattering length. So this is the perturbative proof of Anderson theorem that you can say. And so there is no reference to electron-electron interactions so far, but Anderson, Muttalib and Ramakrishnan studied that problem in 1983. So basically what they say is that, so as we showed that electron phonon vortex is unchanged by disorder, but the Coulomb vortex is enhanced by disorder if we're in the strongly disorder regime. So because of that, so the Tc will decrease sharply after some critical resistance. That critical resistance corresponds to the mobility edge. So there is a sharply fall of critical temperatures beyond some critical disorder. There is a experimental data in indium oxide systems in 1984. What they see in turn that it's not that sharply fall, it just gradually fall. So they plotted that critical temperature versus 1 over kfl square. So they say that it's proportional to 1 over kfl square, and it's a gradually fall, so not the sudden fall. And then there's the calculations Fukuyama Iwishava and Makawa in 1984, and what they say is that not only that electron-electron interaction is increases, but there is a localization change, some kind of single particle change in density of states, and if we consider that, then the change in critical temperature is 1 over kf square in the not so strong disorder regime. But this experiment, although saying 1 over kf square, but the highest kf they have reported is something like 2. So it's not very high kf though. And the recent data of Pratap's group, they are saying that the TC versus KFL is like that, but this is not in their data is up to 10 KFL. So, and this variation of TC is not 1 over KFL square. Sorry.
Is there any physical argument that why beyond certain disorder there is no change in
Yeah. So that is no. That was the Anderson's calculations. That what I am going to say is different.
was there any physical argument?
Yes. So after some critical resistance, it suddenly the Coulomb interaction is very high, so that it reduces the effective interactions which causes superconductivity, and that's why you get. Mm-hmm. No, it was not actually. If you don't include interactions, it doesn't change. That's what.
I think
That
he's
is.
asking for physical arguments for Anderson's theorem. Maybe we can
Yeah.
not Anderson's theorem author.
Yeah.
Something even more physical. No, there are some more physical arguments. I can.
Okay. So there is other calculations of Ghoshal, Mohita, and Nandini in 1998, where the system considered is two-dimensional systems in the lattice model. So that is the Hamiltonian. So we have a disorder Vi on-site disorders, and they decompose that interacting negative Hamiltonian in the delta and delta star, and also there is a reduction in the density, so there is a chemical potential change, and say the self-consistently solve the Bogoliubov-Dijon equations with the box distributions of the disorder in the range minus V and plus V, and they showed that the distributions of delta when the disorder is very low, this it's a high peak, that means there is a uniform delta, but as they changes the strength of the disorder, so the weight changes toward the lower values of disorder, and for the disorder something like 3t or so the weight is maximum is very near 0. So the snapshot of those deltas are like this. So if you change from dt to 2t, then you can show that there is some regime where these deltas are very small, and some regime where deltas are large. So there is a formation of particles, and they further showed that beyond some t, calculating the phase fluctuations, they showed that there are some kind of superconductor to insulator transitions in the absence of Coulomb interaction. And similar study has been attempted by other peoples also. But so basically, then you're seeing that the problem that I'm going to study or discuss. So as you know, there are huge amount of data available near superconductor insulator transitions, and naturally the theorist focuses on that regime, and there is interesting regime. And that is partly because of we have the consensus of validity of Anderson theorem in the low disorder regime. But however, the available data that I showed you that Pratap presented here, that in the low disorder regime also there is is not completely agree with the Anderson theorem. So what my goal is that can one have some kind of consistent theory from the high KFL regime to understand these superconductor insulated transitions. So to start with, so what I will do is we'll proceed beyond the Anderson theorem in the approach of Gorkov to understand the available data that we have in the low disorder regime. So that is the phase diagrams of Pratap's curve. So these green points are they find from the resistivity measurement, and the blue points they find from the STM measurement. So they have found that the delta, and what they say is that so the TC and the T star scale is matching with in the high KFL regime, and they do not match in the low KFL regime. So there is a pseudograph phase over here. So this phase is mostly due to the superconducting phase fluctuations, which actually reduces the TC phase coherence goes away in this temperature. However, the T star scale where delta is 0, that temperature scale is much higher. But in this regime, these two scale matches. So one can say that this in this regime, the amplitude fluctuation is as important as phase fluctuation. Probably amplitude fluctuation is more important than phase fluctuation, and that's why these what I'm going to study is these amplitude fluctuations.
So this KFL in Pratap's data, which is for different samples, and it is these samples are obtained by Niobe sputtering, and so they all correspond to different carrier densities, and so they do have very different screening parameters.
Okay.
So actually we should not directly and blindly apply Fukuyama, and we made that clear in the paper we wrote, that Fukuyama should be used with care in simplification, because you have seriously varying density by a big amount, and you should worry about the change in the electron-proton interaction itself. So one should not take it as a breakdown of Fukuyama's theory.
Okay, that will.
So KFL is fluctuating here.
Yeah, it's not that we are just changing air, the density itself is
Mhm.
It's different from when you start radiating it, have radiation damage, and then these theories are initially aimed at radiation damage where you increase the disorder but don't change all the other values. Yeah. Here it's
different. I think
Yes.
failure point to note that.
Okay, so. So I'll start from the Gorkov's equation again. So that is the Gorkov's equations in the notation of Nambu's-Green's function, G. So that is the Gorkov's equations. So this Green's functions is a 2 by 2 matrix with the normal and anomalous Green's functions, and the other parameter that you can write with the anomalous Green's function, which is this 1-2 component of the Nambu-Green's function. And if I don't have disorder, so that is the Gorkov's equations for the BCS theory. So this is the averaged disorder averaged Green's function. That is the Green's functions in the absence of disorder, and then there is scattering from the disorder and take the self energy. So this is the average Green's functions. But if I don't take full average, so there is the unaveraged Green's function. So this there is two scattering from the 2 points, and I don't take the average. So that I can express the Green's functions. I have two disorders scattering from at the point R1 and at the point R2. And I take the disorder for that the configurations of the disorder is 0, and there is a short range correlations BR and BR prime. So we know from in the absence of disorder, the self-consistent equation that one gets is this BCS order parameter and has that kind of relations. Now if I have the delta of this, now I take the average of that disorder average, then I take the G12 average. So basically this, what I can show is that these Green's function do not contribute anything, so only contributions coming from this bare Green's function. So that's why the right hand side remains same. So so this is in agreement with Anderson theorem that one finds averaging delta R. So basically this is Gorkov's calculation again in some other language. Now what I am going to show is that let's think about these correlations delta of delta R. So that is the deviations of delta R from the mean, from the average. So let's find the disorder average of that quantity. So if I do calculate that quantity, that you can see here that V at 4 points. So I have to take the disorder average of that. So I can so diagrammatically then I can have there are 4 ways. So there are the 4 diagrams. So this is the normal ladder kind of diagrams, and this is crossed diagrams, and there is a scattering from one point. There is a 4 scattering just from one point. So one can calculate these diagrams and show that this diagram and that diagram T1 and T4, the contribution is 0, and but however the T2 and T3 are non-zero. So one can calculate these 2 contributions, and this disorder average. So it's a translational invariant. So there is this function of AQ. That AQ we can express in terms of the coherence factor for the disorders, for the disordered superconductors. So these are the BCS order parameter, and this is the there is a self-consistent equations for the disorder. So there is a change in things that I will show it later, but that is this contributions in the AQ. So if one calculates that AQ, so one can explicitly show that it has the explicit dependence of 1 over tau E square. So actually one can express that in terms of the KFL. So there is an explicit dependence of 1 over KFL square, and there is an S of Q which is a Q dependent. So one can calculate that if I plot the S of Q versus Q and different KFL, and the parameter that I have chosen is delta naught by epsilon F is 3 power 10 to the power minus 4 in the correct regime. Then we can show that as KFL increases, this S of Q increases. So there is that I can show, since AQ is non-zero, so there is a non-zero correlated fluctuations in order parameter, and these fluctuations is in the order lower than 1 over KFL square, because since this S of Q is increases with KFL. So next thing is that I can calculate quasi-particle self-energy, considering 2 kinds of scattering. One is this quasi-particle scattering, so that is the normal contributions, and then there is scattering coming from the induced fluctuations in the order parameter. So that is this contributions A of Q. So if I consider this normal contributions, so for this parameters V square, so we have the electronic scattering lifetime tau E. Similarly, I can define in the same kind of picture, I can define that scattering lifetime of the Cooper pairs, which is tau C. The tau C that is, I can define this way. So that has explicit dependence on 1 over tau E square, and then you have to integrate that S of Q with the cutoff that pi over xi, the coherence length, which depends on the square root of BCS coherence length times the scattering length. So I can integrate that. So if I integrate that, then I can estimate this scattering lifetime of the Cooper pair. So just for the analogy, I just multiplied by the Fermi velocity. So it's kind of some kind of scattering length, and I plotted that 1 over KFL delta versus 1 over KFL. That you can see that that varies with this showing the low disorder regime. So this is 0, so it goes to 0, where 1 over KFL is 0, this is also 0. And if one, so there is an explicit dependence on 1 over KFL square, and the remaining contribution which is coming from S of Q, so that is, you can parametrically, you can fit that, it's some kind of log KFL with some coefficients order of 1 in the large KFL regime.
Sorry, explain. I thought you use single electron self-energies
Yeah,
in the previous.
you're right.
How did you get the average lifetime of a Cooper pair by studying one particle self-energy?
So, yeah, so basically, so basically my thing is that similarly you have the V of R prime, so that is non-zero. Similarly, that what I will show is that these fluctuations delta R prime is non-zero. Non-zero. So if you have the single electron scattering, up goes to this, and now you have this, because of this you have some kind of scattering with k of things to minus k with the down spin, and then you have again minus k plus q, and then again k of kind of things. So because this is non-zero. So because it's scattering, so you can define some kind of lifetime. This lifetime, I mean the lifetime is in the scattering lifetime. So the sorry. Yeah, because it's a huge lifetime. It's not that it's a huge lifetime compared to the electron lifetime. That you can see here from the data you are seeing here, the ratio of these two lifetime is 4 orders of magnitude higher for these Cooper pair scattering.
Because the question is, if you're speaking about lifetime, you need to give somewhere to put something on the match cell. So, because the question is, where is
Perpendicular to what? I mean,
for example, the very quasi-particle or whatever.
Mm-hmm.
And there's
So it's yeah. So it's basically the so the minimum time it takes to scatter from the non-uniformity of the disorder in the delta.
I mean, don't you have to look at a two-particle propagator and look at some imaginary part in order to get a Cooper pair lifetime? How can you just look at a single particle self-energy and pull out of that Cooper pair lifetime?
Asserting that where the properties were seen that characterized by some particular form, and that particular form has something that calculates in terms of it's an assertion sort of form was
Right.
which already implies that in the lifetime.
Yeah. So let's. So I've defined some kind of scattering lifetime for the Cooper pairs, and then what we have that effective actions for the disorder, the del square by u, and then the trace over log Green's functions. So this is the Green's functions for the disorder dr and then delta r. So one can take the saddle point equations by minimizing this action. So that is the saddle point equations, and you take the average disorder average of these equations, then you have the disorder average Gin's functions, and this disorder average Gin's function has contributions from the two kinds of scattering. So there are two kinds of scattering lifetime, 1 over tau e and 1 over tau c is coming. So instead of the new type of scattering, if I don't consider that, then we know that this frequency and delta has is equal actually. So if I don't consider tau c, it's 1 over tau c is 0, then this is equal. But because of the presence of that, now this there is not this kind of simple equation, and so this z bar and delta bar is as follows these equations, but one can solve those equations to find these ratios of the delta bar delta and z bar by z with these two numbers, and the two numbers has a dependence on the f, which is the ratio between two lifetimes, and which is very small compared to 1. So I showed that it's like 10 to the power minus 4. So there is small deviations from BCS result. So if one can find that order parameter at 0 temperature, so I have to solve the self-consistent saddle point equation in the presence of these two kinds of scattering, and so that is the self-consistent equations. So I have now a new type of term over here to tau c times omega square by delta plus omega square. So if I don't have that term, so that is this BCS kind of equation. So that we know that, so that is the result. But since I have that kind of term, so I have these equations follows like a delta over delta is pi over 2 tau c times delta. So the approximate solution of that will be delta naught pi over 2 tau c. So the order parameter depends on a disorder, even for low disorder regime. Mm-hmm. Okay, let's. So similarly, I can find that critical temperature, which is actually in the present day's language, it's a T star, not the TC. So T goes to TC is delta goes to 0, and then the self-consistent equations will have that kind of equation. So if I don't have that tau c term, so you know that that is the BCS result, and that BCS result is this is the TC. But now I have that kind of term, so that follows these equations in terms of the digamma function. So this TC is also decreases due to the disorder, and so this tau c I can express in terms of kf L delta. So that is the kf of L delta, and that I have already shown. How does it? Sure. Yeah. So this is the variation of TC with KFL that I find, but although this looks like the experimental data, but it's not interested if the validity of whole theory for the whole range of disorder. So that you can see from the if I see the data from the theoretical data and I vary TC by T versus 1 over KFL, that that it's a linear, at least in this regime, starting from less than 0.1 to something over here. It's close to a linear. And if I replot the data of Protap's group, TC versus 1 over KFL, that also shows some kind of linear in this regime. But if I want to fit that thing, in the linear fit, it doesn't fit from this regime to that regime with a linear function, but actually fits some kind of this kind of form where there is explicit dependence on kfl delta is 1 over kfl square, and the remaining term is some kind of logarithmic 0.45 kfl, and it turns out that in this regime of kfl, it behaves like whole term is 1 over kfl. And so the data is also showing that some kind of linear dependence or 1 over kfl. And so the old data is also showing some kind of that kind of dependence, although this result is, this data is for not so high kfl. So this
L delta top one.
yeah, so that is the scattering length for the Cooper pairs, other the mean free path for the Cooper pairs.
That's something you calculated, or that's a free parameter?
No, that's a calculated from the right.
So what is it when you calculate?
Yeah, that right. So that is these things. So 1 over kfl delta is okay. So yeah, so I think so what I am saying is that so this my calculation is things the similar linear behavior up to this kind of phase diagram up to 0.3. So okay. So now I just calculate the density of states. So density of states has also dependence on these complicated ratios of this delta over delta. It has this, but that dependence doesn't have much contributions because these f's are very small. But the main contribution that is coming because of this delta, and that delta it changes with the disorder pi over 2 tau c, and so if one replaces this eta by this parameter gamma, which is the generalized Dyne's formula, and the outcome of this density of states is that because this delta depends on the disorder, so there is a shift of the coherence peak towards the lower energy as we increase the disorder. So that is the plot that I get. So for the zero disorder, there is a coherence peak at the BCS value. So you have delta is not at 1. If one changes the disorder, so 1 over kfl is increasing in this way. So you can see that there is a shifting of coherence peak. So similarly, they find in the experiment there is a coherence peak with the samples which has TC lower. So some kind of qualitative agreement. And now if I calculate 2 delta over Tc versus Tc over T naught, Tc naught, so while Tc is equals to Tc naught is the BCS limit, so the value is 3.52, and then it's gradually increasing with the increase of disorder. So as the Tc decreasing, so it gradually increases from 3.5 to something order of 5. And the experimental value is somewhere near 4.1 in that regime they did the experiment. So finally, I will just give the summary. So I have static disorder that induces the some kind of correlated fluctuations in the order parameter, and that enable us to define some kind of average lifetime of a Cooper pair, and that has been estimated. And there is self-consistent equations for the order parameter that suggest some kind of reductions of the value of the order parameter with disorder. Then I find the critical temperatures which is also decreasing with disorder. There is a shift of the coherence peak towards lower energy as we increase the disorder. But however, there is no reference to electron-electron interactions in my calculation. So the role of the interactions, electron interactions will increase as we increase the disorder, and that probably will help to reduce the fluctuations, correlated fluctuations of the order parameter, and that could in turn help to the observed flattening of these T-star scale over here, up beyond that. So that is probably maybe the scenario of this. So, and at so what I find is that at low disorder T star is the TC, because the T star would be less than equals to the T phi, which is phi is the temperature scale coming from the phase fluctuations. But however, as disorder increases, the superfield stiffness decreases, and hence the phase fluctuation will be important and at high disorder, and there the TC will be the T phi, not the T star. So finally, acknowledgement. So Professor T.V. Ramakrishnan has introduced me to this field, and he had a lot of suggestions. So thanks to him. So with that.
For questions? Okay, if there are no questions, there was a question from this young man about more physical interpretation of Anderson's theorem. With your permission, I will make
Sure, yeah.
See, you should read Anderson's paper. It's a remarkable paper, because some people wonder why it's called a theorem. Because there is no statement of theorem, no proof, but lot of physical intuition and some mathematics guided by the physical intuition made that classic paper. So what I understand is the following. So a very important component of that paper is this time-reversed eigenstates. So if you have no disorder, they are basically block states running in opposite directions. Now once you introduce disorder, these block states get modified. Now as long as the modification is not large compared to the coherence length, you can think about meaningful coherent propagation within the Cooper pair size. Now what it means is, before the block state gets modified by scattering, it gets correlated with the next electron and they start cohering. That's why these things overlap and you have macroscopic coherence. So this is my understanding. Experts can correct me. But if there are no further questions, we thank you once again. So now we will adjourn for tea and come back at 11:15. 11 is official time, but up